I have some organizational things to say. Basically, there will be recordings available on YouTube. There will be a Discord channel for questions and discussions. I will check it regularly. And in addition, there will be notes available in my webpage. The recording of last time is missed something like 5 minutes. So I'll just repeat the introduction I said back then. Amatan. Oh, I see somebody cannot hear. Do you know what? This is for the recording, so it should raise your mic. So I should. Is it okay now?
Yeah, it's good. Yeah.
Okay. So Amatan. Most of my life, I did mathematics in academia. I did a PhD in the Hebrew University of Jerusalem, and then a few postdocs in Europe. And 2 years ago, I started working in cryptography, and there seemed to be a need for a mathematical background for people working in the field, and that's how this course emerged. I now work for the Ethereum Foundation. This is a course that is hybrid. Partly, participants are in the Ethereum office in Berlin, and some online. So we will meet on a weekly basis for 2 hours, and this is expected to take something like a year. Last time I gave a motivation and overview of what we do in the course, and today I will start talking about sets. What happened historically is that in the early 20th century, mathematicians discovered a growing number of paradoxes, and as a result, they got into a project of new foundations for mathematics. And they converged to what is called now set theory as the solid foundation for all modern mathematics, but also incorporating all the previous corpus of math, apart from very small things that were discovered to be wrong. And the formal set theory is called Ceremelo-Frankel. Choice, and this is abbreviated as ZFC. And this is a set of axioms that is that is now the standard foundation of math, and in which basically all modern mathematics can be written, and also theoretically, let's say, can be verified by a computer. So basically, it's a set of axioms and deduction rules, and every mathematical statement can be written as every proof can be written as a sequence of deductions from the axioms. So it could, in theory, be checked by a computer. So this gives a very solid foundation of mathematics, and what most mathematicians think about logic is it's good to know that we have solid foundations, and that in theory we can prove all the stuff that we do in a computer and so on. But other than this, we don't care. And set theory is a research domain for logicians. But this is a very small fraction of the mathematical community. Maybe an interesting fact is that Frankel was one of the founders of the math department in Jerusalem. So Jerusalem typically have a strong mathematical logic group. What we will do is what I call, or what is typically called, naive set theory. And what I mean by that is we're not going to write down all the axioms and be very formal. This is not very useful, but we will still talk about sets, because they are fundamental in every mathematical treatment. And the slogan here is that sets are the machine code of modern mathematics. And now, what is a set? So, from the axiomatic point of view, we have a language, a logic, in which we can write statements. The way to write statements involves a bunch of symbols. So we will write this symbol, this is for all. And then we have exist. Negation, implied, or if then, implied and being implied. This is called if and only if. And did I miss something?
Not element of?
We will soon get to the element of. Yeah, so this is basically the logical symbols in which one can write statements, but we will often replace some of these symbols by words. So this is for all. This exists. And this is not. This you could say if then. And this is if and only if. And I will abbreviate this as if sometimes. So a set S is a collection of elements and the syntax to write a set is with curly brackets and then the specification of all the elements. Let's say a typical way to write a set one is that you can specify all the elements. I mean, this is of course possible only if S is finite. Let's say 1, 2, and 3. And you see, I put curly brackets in the beginning and the end, and I separate the elements by a comma. Another way to write a set is by some rule. So I can write S is the set of all n such that n is bigger or equal than 2. So you see here I have a formula. This you can regard this part as like the entry condition to the set, and entry conditions are written in logical formulas. Of course, I don't want to be too formal, and sometimes instead of writing the entry condition in this way, I can write S is the set of all numbers 2, 3, 4, and then 3 dots. 3 dots means it's an abbreviation instead of writing a formal entry condition, where the entry condition should be obvious for the reader. Now, one of the syntax we have for sets is that for every object X, either X is an element of S, in which case we write X belongs to S, or X is not element of S, and then we write X does not belong to S. Okay, so this is the basic syntax of sets. And one thing that is important to notice, I mean, sets or maybe when considering elements in a set, we ignore repetitions. That is, for example, the set S is specified by the following formula is equal to the set 1, 2, 3, right? And the order of elements, the order or the collection of elements in S has no particular order. So what I mean by that is that the set 1, 2, 3 is equal to the set 3, 2, 1. Okay, so if a set S is finite, we write hash S for the number of elements in S. And again, I ignore repetition, right? So in this case, for example, the number of elements in S is 3. And we say that two sets say S is included in T, and this is denoted as S in T, if for any element small s in big S, the element small s is in fact in the set T. And note that we have for sets S and T, S is equal to T if and only if S is included in T and this is T is included in S. Okay, so this kind of observation, although trivial, is a very useful tool to break the equality into two pieces. It's a bit like you can say that two numbers n and m are equal if and only if n is smaller or equal to m and m is smaller or equal to n. Okay, so this is another a way to break the equality between numbers. And with regard to sets, we have basic operations. One of them is the union. I take, let's say, a sets A and B, and I define the union. This will be my notation for definition. I define the union to be the set of all x such that x is an element in A, or, and this is an inclusive or, x is an element in B. Right? So potentially x could, when I say inclusive, I mean potentially x could be an element in both A and B, and this would still be considered an element in the union. And in mathematics, we always use inclusive or, and the notation for this is this V. And I can also talk about the intersection. If I have two sets A and B, then the intersection is the set of all x such that x is an element in A and x is an element in B. And I can also talk about the difference or complement. And this is A minus B is the set of elements x that belong to A but do not belong to B. Any questions about this part? Yes.
I have a question about the first precondition for a set that you. The superset is the set of natural numbers, right? Is that implied by the small n, or?
Oh, you mean this in this?
Yeah, n bigger or equal.
Yeah, I didn't mention. I will soon talk about famous sets, but
Okay.
yes, if I wanted to be precise here, I should have said n is a natural number,
Okay.
and n is bigger or equal to 2. Yes.
Okay, thanks.
So this is a good reminder. Maybe we talk about some famous sets. So the first, as was mentioned, this is the natural numbers. 1, 2, 3, and so on. Then we have the integers. This is 0, 1, -1, 2, -2, and so on. We have the rationals. This is the set of all quotients A over B such that A and B are integers and B is non-zero. And we have the real numbers. I guess one way to quickly define it is the set of all decimal expansions. So it's all numbers of the form A dot A1, A2, and so on, such that A is an integer, and for every I bigger or equal to 1, AI is a digit. Yes.
Apparently, there's some confusion whether 0 is a natural number or not. Sometimes apparently it is, and sometimes it's not. What's
Yes.
our definition?
So in my convention, it is not. This is typical typical convention, but it's true. In some places it is included. Apart from the real numbers, we can also talk about the complex numbers. I don't know if any of you, I assume that you heard about this, but I will define it. This is all the numbers of the form A plus BI, such that A and B are real numbers. So this I is like a formal symbol. And we will talk about, later we can talk about the operations of complex numbers. It's not hard to define, but for now we only care about sets. So this is the set of complex numbers. And of course you can see that I have inclusions. Coming back to union and intersection, I don't have to do a union or intersection only of two sets. I can take any collection of sets. So of course, if I define union and intersection for two sets, then inductively I can define it for every finite number of sets. But even if I have an infinite collection of sets, I can talk about the union of this collection and the intersection of this collection. How do I do it? I simply generalize the formula. So, maybe a quick question. Yes. Yeah. But speak up.
Could you please highlight the difference between the rational number and the real number? Because it seems like it's
so. So you see in the real numbers, the decimal representation, first of all, need not be finite. Okay, maybe we start with the rationals. The rationals are all quotients of integers. Okay, and it's true that every quotient of integers you can have a decimal representation. And this is the reason that the rationals are included in the reals. But it is not true that every decimal representation, and especially, I mean, basically only if it is infinite and non-repetitive, so like pi cannot be, pi has a decimal representation that does not have any cycles. I mean, does not have any fixed cycle that you can. In this case, I mean, this needs to be proven and so on, but it is not a rational number. It cannot be. And now we will talk about. I mean, the Greeks thought that all possible numbers are rational. And then there is a famous proof that the square root of 2 is not a rational number. Okay. So for us, this is a quick definition, but in fact, we will not deal a lot with the real numbers and the complex numbers. We will talk about them for intuition. But what we do is finite fields, and then reals and complex numbers are not used. Coming back to the union and intersection, if I is an index set, is, let's say, a set that you can think of as a set of indices. And for every I in I, we are given a set AI. Then we can define the union of all the AI. This is denoted like this: the union over all the indices, the union of all the AI for every I in I. This is the set of all x such that there exists an index I in I for which x belongs to AI. You see what I did here? I used the syntax that allows me to write a condition, an entry condition to the set with the logical symbols, and this is a valid definition. And dually, I have the intersection of all the AIs. This is the set of all x such that for all I in I, x belongs to AI. Okay, so if I am allowed to write a formula I can also do this, the following trick. I can define the empty set. It is denoted by phi, and it is the set of all x such that x is not equal to x. Okay, it's a legitimate definition, and of course the number of elements of the empty set is 0. But in fact, and this is maybe a nice thing from the foundational point of view. I can define all the natural numbers using the empty set. How do I do it? I define one. So suppose we are like in a world in which we only have the sets and the basic operations that we talked about. So in particular, I have the empty set. I can define, before I define 1, I define 0 to be the empty set. And I define 1 to be the set whose unique element is the empty set. And I can go on. I define 2 as the set with 2 elements. One of them is the empty set, and the other is the set containing the empty set as a unique element. In other words, 1 is the set containing a unique element that we previously defined as 0. And 2 is the set containing 2 elements that we previously defined as 0 and 1. And generally, I define, assuming that I defined the number n minus 1, I can define the number n as the number n minus 1 union the set containing as a unique element the number n minus 1, which in other words is the set of all previously defined numbers or natural numbers. Okay, so this is just, it's not, we're not going to use this definition. This is just to show you how mathematics can be constructed completely from sets. I mean, in this way, we define, this is inductively. So I get the definition of the natural numbers as sets. And we will see later how you can define the integers and the rational numbers as sets as well. We will not do the construction of the real numbers, but there is a way to also construct the real numbers as sets. So in this fashion, you construct all the basic mathematical objects as sets from the empty set, right? This is like an anchor, and then this gives you a way to view all the mathematical corpus in this axiomatic way. Any questions? This is, so N is of course a set of sets. Yes.
Yeah, I had actually a question about the definition of the empty set, because it's defined as elements that are not equal to themselves. But if you take, for example, in JavaScript, I think it's JavaScript, there are some languages where you have objects like NaN, not a number, so clearly that's not a number, but it's still something that is conceptually understood. Not a number is not equal to itself. So yeah, I mean, maybe I'm missing something, or I'm trying to apply something that doesn't really belong. But it seems to me that it doesn't quite work.
Well, I mean, we are not. Mathematics separates itself from any real world domain precisely for the purpose of being decisive. And so, I mean, on the formal level, there is an axiom in set theory, in ZFC, that says that every x satisfies x equals x.
Right. So I guess for my counter argument to be receivable, we would need a formal definition of JavaScript objects.
Yeah, I mean, eventually, once you put this, basically in every logic, in every mathematical logic set of axioms, you have this axiom that x is equal to x for any x. Otherwise, it doesn't make any sense.
Gotcha. Thanks.
Okay. So now, what can we do with this syntax of sets? I mean, this is a nice thing to be able to define the natural numbers. I now want to be able to talk about ordered elements. I mean, remember the elements in a set are not ordered, but many of the mathematical objects we deal with require some order of the elements. So an ordered, so let's put it like this. Given two objects, A and B, the ordered tuple of A and B is the set, I will call it OAB, and this is the set that contains two elements. One of them is the set containing the unique element A, and the other is the set containing two elements A and B. And this, I mean, of course, we will not eventually use the this formal definition of ordered pair ordered tuple or ordered pair. But this is another demonstration for what we can do in sets and the power of the syntax we have. So the observation here is that for objects A, B, A prime, B prime, OAB is equal to O, A prime, B prime, if and only if A is equal to A prime and B is equal to B prime. So how do I prove that? We have two directions to prove, right? So let's say if OAB is equal to O A prime B prime, then I take an element in the set in the left hand side, the set A is an element in OAB. So this must mean that the singleton A is an element in O A prime B prime, which I remind you is the set containing the singleton of A prime and the two set element A prime and B prime. But the singleton A is a set with one element, so it cannot possibly be equal. So the singleton A must be equal to either the singleton A prime or to the other element, which is the set with two elements. But this cannot happen, right? The singleton A, a set with one element can never be equal to a set with two elements. So we must have that the singleton of A is equal to the singleton of A prime. And since these are sets with only one element, I get that A must be equal to A prime. If A is equal to A prime, then I also know that the set A, B is another element in OAB, in the ordered pair of A and B, and therefore I know by the assumption that the set A comma B must be an element in the set, in O. In O A prime B prime, which again I remind you is the set with these two elements. And this means that by the similar argument that AB must be equal to one of these two elements, but it cannot be equal to the first element, to the singleton containing only A prime, because A comma B is a set with two elements. So it must be equal to the other set with two elements, A prime, B prime. But since we already know that A is equal to A prime, and we must have B is equal to B prime. Okay, so this is the implication. What I mean, if I know that OAB is equal to OA prime B prime, then I necessarily know that A is equal to A prime and B is equal to B prime. I'll just write it again. OAB equals OA prime B prime implies A is equal to A prime and B is equal to B prime. Conversely, if I know that A is equal to A prime and B is equal to B prime, then clearly OAB is going to be equal to OA prime B prime. Right? This is look at the definition of OAB. If A is equal to A prime here, if A is equal to A prime and B is equal to B prime, then immediately I get that OAB is equal to OA prime B prime. So this concludes the proof. Yes.
Can you hear me?
Yeah.
Yeah, but this only works if you have an enumeration between those two sets, right? Like if you can count the elements.
Yeah, but okay, so I mean, I don't want to be bogged down too much in the axiomatic setup, but kind of the underlying assumption is that I can recognize, a set with one element and a set with two elements.
Yeah, but if the set is infinite.
No, I mean, A itself could be, A itself is just an object, but A could be an infinite set. But the set containing A as a unique element is always a finite set. You see what I mean? I mean,
yes.
like the set containing the natural numbers as a unique element is the number of elements in this set is 1. Okay, so this is kind of the syntax that you need to get used to. Right? We can talk about sets as elements in other sets. Okay, and in fact, from the axiomatic point of view, that's all you can do, because all your objects in the universe are sets, and you can define a set of sets and a set of sets of sets and so on. Okay?
I have another question.
Yes.
Having the set A is equal to set A prime, from the number of element perspective doesn't imply directly that A is equal A prime.
We said that a set A is equal to a set B, if and only if for every A in A must be in B.
Yeah.
So,
how do I know that A prime is?
so I take this A, it is in A, right? And it must be an element here.
Yes.
But there is only one element in the right hand side. The one element is A prime.
Oh yeah.
Okay.
That's an axiom.
So if A belongs to the set with one element A prime, then it must mean that A is equal to A prime. Okay. So we will denote notation. I will write A comma B for this OAB. And this is the ordered pair of A and B. It is a mathematical object that has the property that if you take four objects, A, B, A prime, and B prime, and then you have equality of the two ordered pairs if and only if A is equal to A prime and B is equal to B prime. And notice that we needed a new object for this property because the set A comma B does not satisfy this property. I mean, because it could be that A comma B is equal to A prime B prime, but for example, A is equal to B, A is equal to B prime, and B is equal to A prime. Right? So it's because this sets do not encode the order of elements, right? So we need a new mathematical object that does take care of the orders. Any questions before we take a break? Okay, so let's take 10 minutes break. You can look at the notes and so on and come back with questions about what we did. What we did with ordered pairs. All right, so
maybe one simple question.
Mhm.
If it has the ordered pair has three elements, is it then the superset of set with A, set with AB, and set with ABC?
No, the ordered pair is a set with two elements.
Always, regardless of the number of elements, no.
Regardless of the number of elements A could be a set with infinite elements, B could
True.
be a set with finite elements, but OAB is a set with two elements. You can know that because there is one comma.
Okay, thanks.
Okay. But indeed, if you look at that's the issue. All right. So given this notion of ordered pairs, we can talk. So if A and B are sets, in the Cartesian product of A and B is the set A times B, the set of all tuples ordered pairs A comma B, such that A is an element in A and B is an element in B. Okay, so this is this was invented by Descartes, the philosopher, and it is one of the cornerstones of the modern set theoretical treatment in mathematics. And for example, I mean, maybe a simple example, I take A to be the set with 0, 1, and B the set with 2, 3. Then A times B, it has 4 elements, and they will be 0, 2, 0, 3, 1, 2, and 1, 3. Right? Because I allow every element in A to be in the first coordinate and every element in B to be in the second coordinate. Now, it's useful to see what happens geometrically. So let's say A is, this is called the unit interval. It's the set of real numbers that are bigger or equal to 0 and smaller or equal to 1. And let's say B is the interval 2, 3. Right? This is the set of real numbers that are bigger or equal to 2 and smaller or equal to 3. Then I take the interval A, I put it on the x-axis. The interval B, I put on the y-axis. So this is 0, this is 1, this is 2, and this is 3. And A times B is this purple area. Maybe I should have said, if I take, I take A is equal to the real numbers, B also equal to the real numbers, then A times B is what we call the plane. This is denoted as R times R, or R square. And this is formally it's the set of all A comma B, such that A and B are real numbers. the set of all ordered pairs of a real number in the first coordinate and real number in the second coordinate. And we have a picture for this. We denote by this x and y axis, and a point here typically is a comma b. Right, and so here, if a and b are only subsets of the real numbers, then a times b is going to be a subset of r square, and the picture is written here. Any questions about the Cartesian product? Okay, so using this notion of Cartesian product, I can define the following. Given two sets, A and B, a function f from A to B denoted f colon A arrow B is a subset of the Cartesian product A times B, such that two conditions are satisfied. One is that for every A in A, there exists B in B such that the pair A comma B is an element in F. And two, if A comma B is an element in F and A comma B prime is another element in F, then B is equal to B prime. This is a formal definition of functions, and let me give the informal definition. A function f from A to B is a rule that associates to every, let's call it input element A in a unique output element B in B, and B is denoted as f of A. So f of A is simply a notation for this output element. So you see, informally speaking, I think of A as the set of inputs and B as the set of outputs. And a function is a rule that gives for every input a unique output. So it has to be defined on every element of the declared set of inputs, and it has to give a unique output for that input. So here in the formal definition, if you look at it, this is just saying the informal definition in the language and the syntax we have in set theory. What do I mean by that? I mean, instead of saying a rule, because I don't know what is a rule formally speaking, so a rule would be simply a collection of tuples, a collection of ordered pairs. The first coordinate in the ordered pair needs to be in the input set, and the second in the output set. And the two conditions are exactly saying, well, the first condition says that for every element in the input set, there exists an element in the output set such that the ordered pair is an element in the function f, and two, that I cannot have, the second condition basically says that for every input, so the first condition says that for every input you have an output, and the second condition says that for every input the output that exists is unique. Is this clear? Is this now
the question, can there be an edge case when B is empty?
Yes, and then there will be okay. If it could also be that A is empty, right? If A is, let's start with A. If A is empty, then A times B is necessarily empty, right? And if B is non-empty, we have a unique function from A to B, so from the empty set into B, and this is completely legitimate because what I need is a collection of pairs. I mean, a subset of A times B. I take F to be equal to the empty set. This is a subset of A times B, and it satisfies the two conditions. Okay. For every A, we say in mathematics that it satisfies it vacantly, because the first condition is for every A in A, something needs to happen. But if there is no A in A, then the condition is vacantly satisfied, right? And the second condition says, if I have a pair A comma B in F, then something needs to happen. This condition also is satisfied vacantly. On the other hand, if let's say B, okay, let's say A is not empty, and B is empty. Then, of course, as before, we still have A times B is equal to the empty set. But now there is no function f from A to B. There can be no function from A to B. And why? Because you can see it intuitively. If A is a non-empty set of inputs, I need to give you for every input I need to give you some output, but I have no output to give you. So then there would be no function.
Quick question, maybe.
Yeah.
Are elliptical and parabola also functions?
Not exactly. So okay, so this is a good opportunity. Let's go back to the what is called real valued functions and see what is a function and what is not function. So I take f from the real numbers to the real numbers. Let's say f of x is equal to x squared. This is a function. This defines a function, right? For every x, for every input x, I give you an output x squared. The output is a valid element in the. I forgot to say this is called the domain, and this is called the range of the function. But if I look at let me just draw it like this, a circle or ellipse. I mean, this the circle of radius 1 is the set of all tuples x, y, such that x squared plus y squared equals to 1. This is not the graph of a function, right? Because it's not a graph of a function. I cannot write it. There is no f such that let's call this C. The graph of f is simply f in the formal definition, and there is no function f. Let's say f of x, whose graph is the circle, and the reason is, I mean, you take a 1x and you need to give it two outputs, right? For this x, you will need to give two outputs in order to create a graph. So you can separate it into two functions. This would be the graph of one function, and this would be the graph of another function, right? Or you can separate it in other ways, right? And the same goes for an elliptic curve. Elliptic curve is a solution set. It's like the circle. It's a solution set of a polynomial in two variables, and you can separate it into two functions, and we will do it, but this again, it will take time. If you have, let's say, something like this, then you can separate it into this and this. And the equation, I mean, you have y squared equals, maybe put it here, have y squared equals x cubed plus ax plus b, with some condition on the a and b, and you can write y equals square root of x cubed plus ax plus b, and the one below would be y equals minus x cubed plus ax plus b. And then these are functions. So y, in this case, I could write y as a function of x. Right, and these would be functions from the real, we can say from the real numbers to the real numbers, or we could say from the positive real numbers to the real numbers. Maybe a remark. How do we know that two functions are equal? So two functions f from a to b and g from let's say b, or not b, from c to d are equal if first I need that the domain and the range of these two functions would be equal. Okay, so a must be equal to c and b must be equal to d. And two, I need that for any a in a, f of a is equal to g of a. Okay, that's it. This, of course, this is equivalent to say that as subsets of the Cartesian product, they're equal. So f is, this is the same saying f is equal to g as subsets of the Cartesian product a and b, because fa is, remember, fa is this b. This would say, this would tell us that a comma b is a legitimate pair in f, and this would tell us that a comma b is a legitimate pair of g. Right? So it's the same. But note something important is that I could potentially define the either the domain or the range of a function to be different than example.
And maybe a question with the first point, A is equal to C, the start domain being equal. I would just want to know if there is any function where the start domain can be different but produce like the same answers?
I mean, I could, okay, so this is the example. I mean,
if I take maybe the,
yeah, I can look at f from the real numbers to the real numbers, x goes to x squared. Right? This we said.
Maybe the second one goes from the complex number to real number.
But I don't even have to go that far. I can do from the positive numbers.
Yeah.
Let's say r bigger or equal to 0 to either r. Let's do in this case, and the formula is the same, right? X goes to x squared. These are two different functions, okay? Even though their formula is the same. And even a third function, I go from the real numbers to the non-negative real numbers. And the formula is the same. X goes to x squared. Right? I can do this because I know that x squared is always non-negative. And f is different than f prime. And f prime is also different. They are, f prime is different than f double prime. And f is also different than f double prime. These are three different functions. So you can think of it like in a type language, like in C. A function, I mean, if the output is declared to be an integer or declared to be a float, it's a different function, right?
Yeah.
So this is this is the convention about functions in mathematics as well. Yes.
So to that same extent, you know, when you said the elliptic curve, it cannot be a single function because you've got, let's say, negative side and the positive side. We could actually just define a function that goes from r to r squared, and you know, give like the output would
Yes.
be a tuple that would be plus and minus. But in that case, what you mean is that it's not, the tuple is not the same range, and therefore, actually, could it not be actually? No.
So it's a good point. I could define, and this is called the parametrization. I could define a function from r to r squared that whose image, whose graph, kind of is the elliptic curve. For example, if you want to do it for the circle, you can define t goes to, I think it's cosinus t, sinus t. Right? And so this is a function from r to r squared. You can even say, do it from the interval 0 up to 2 pi. But you can simply repeat it, right? Because cosinus and sinus are periodic. And the image of this function, I mean, will be exactly the circle, because cosinus square plus sinus square is always equal to 1. Okay? So you are right. I mean, there is a function for which the elliptic curve or the circle are the image of the function, but it's not a function from R to R. So maybe to be precise on what I meant earlier, elliptic curve and circle cannot be described as a graph of function from R to R.
Okay, thanks. Yeah, that makes sense.
Okay. Right. So given two functions, say f from A to B and g from B to C. Their composition is the function this is it's simply a notation. This is G composed F. It's a function from A to C, defined by yes, A to C, defined by a G circle F evaluated on an element A is G evaluated on F of A. Okay, so this is exactly what you would think that a composition of two function routines in a programming language does. Right? You need that the input of the second function of G would be exactly the output of the first function, and then you can plug it in. And this note that we say F composed with G, but we write G circle F. Okay, so this it's a bit confusing, but that's the convention, and the reason is because of this formula. It's convenient to write the G circle F. Proposition. If f is a function from A to B, g is a function from B to C, and h is a function from C to D. Then a priori I can do two things, right? I can do H composed G and all that composed F. And I can do H composed G composed F. And the proposition claims that these two functions are equal. Okay, this is called associativity. Associativity of composition. How do we prove associativity? This is very easy. I mean, remember, we need to show the two functions. We have two functions, right? The left-hand side and the right-hand side. And we need to show they are equal. How do we show they are equal? Well, we need to say, we need to show that for every input element, the two functions agree. So H composed with G composed with F evaluated at A is equal to H composed G composed F evaluated at A. So it's a lot of brackets and we need to start peeling them off. The left hand side is equal to H composed G evaluated at F of A, right? And this is equal in turn to H evaluated at G evaluated at F, or F of A. And the right hand side is going to be similar. I first do, so this is H of G composed F evaluated at A, and G composed F evaluated at A by definition of composition is H, this is G of F of A. Okay, so we get the same expression. What else? Any questions about this this notion of composition and functions? All right, so maybe one more thing before we end. For every set A, there is a function which I will denote as the identity A. This is a function from A to A, and defined by identity A evaluated at an element A is equal to A. Right? This is the function that doesn't do anything. And exercise. It's a very easy exercise. For every function f from A to B, now I can do two things. I can take f and compose it with the identity function on A. This is like, diagrammatically, it means I do the identity function on A, and then I do f. And I claim that f composed with the identity function on A is equal to f. And the second thing is I can take f and then I can do the identity function on B. This is diagrammatically, it means I do f from A to B, and then I do the identity function of B from B to B. And this is also equal to F. Okay, so I guess this is what I wanted to cover for today. Are there any questions or requests for next time? Okay, and see you next week.